Welcome back. Today, a real treat. The starter motor. These are all the parts of the starter, and the engineering in there is so tasty that I've included a knife and fork. For f***'s sake. A knife and fork is perhaps my favourite little bit of engineering on this car. Elegant in its design and extremely reliable. So today we're going to build this starter from its parts, and then you'll know exactly how it works. We'll get to explore all sorts of new mechanisms, solenoids, planetary gears and sprag clutches. So stick with me, we're covering a lot more than just starter motors here. Why do we need a starter at all? Well, it's because an engine can't start itself, and this applies to most engines, not just car engines. You might have seen little starter trucks driving around at airports starting up planes, or you've pulled the cord to get a lawnmower started. Now, all internal combustion engines need some help to get moving, and that's because only one of the 4 strokes in an engine generates power. That's the third stroke, the power stroke. The engine could have stopped at any point with its pistons in any position, and to start again we need to get back around to a power stroke, and that is the job of the starter motor, to turn over the engine, taking it through the unpowered exhaust, intake and compression strokes until the power stroke is reached and the 4-stroke cycle is able to run for itself. Now, the first cars were started with a hand crank. Turning a handle attached to the crankshaft would take the engine through those unpowered strokes. But this was hard work and potentially dangerous too, because the handle had this tendency to be unpredictable. So broken hands, ribs, legs were all risks of starting your car. And it's a great example of what an extreme sport motoring was back in the day. A strong likelihood of a crippling injury before you've even got moving. So safety measures were added, but this was far from ideal. Various other methods of starting were attempted using coiled springs or compressed air, but from 1912, every Cadillac included an electric starter motor.
Cadillac and a man named Kettering found a way to start a car electrically with the push of a button.
Theoretically, this damn thing ought to work now.
The design of starters has been fairly standard since then, and certainly since the 60s onwards, starters were of a near universal design like this one that we have here. Now, there's been a bit of change lately because we have stop-start engines which use a different type of starter which also functions as an alternator. I'll make another video on that later as soon as I can convince someone to give me one to dismantle. But back to our classic starter. The starter has a small gear called a pinion which interlocks with the teeth on the outside of the flywheel. Inside the starter is a very strong electric motor which turns the pinion, which turns the flywheel, that turns the engine and hopefully gets it started. I'll install this temporarily so we can see it in action, and then we'll pull it to bits and have a closer look. Normally, the starter fits to the transmission casing on this car, so we'd have a whole bell housing here and we wouldn't be able to see anything. So I've made this bracket, and I've also cut away a little piece of the starter housing here so that we can see inside. One thing that we can immediately see is that the pinion gear is much smaller than the flywheel. Compared to engines, electric motors turn very fast, but they don't generate much torque. That is, they don't have a lot of turning force. Now, to turn the engine over takes a lot of force, and this small motor has to move a load of metal to get the engine started. It's got the flywheel, the crankshaft, the harmonic balancer, the alternator, the power steering pump, 4 connecting rods, 4 pistons, the timing gear, the camshafts and the valves, and all in, I reckon that's at least 120 pounds or 50 kilos. And it's compressing the air-fuel mixture, which makes things even harder. And the engine needs to turn over at a decent speed to get it started. Any less than about 100 RPM and there's not enough suction or compression created inside the cylinders. Now our flywheel has 112 teeth and this pinion has 8. This reduction in gearing means that on this engine, the pinion turns 14 times for every turn of the flywheel. Or, in other words, the torque from the motor is multiplied by 14 times. Let's take a look inside the motor itself. Even after the reduction in gearing between the starter pinion and the flywheel, we still don't have enough torque to actually turn the engine. So inside the motor is a planetary gear set, which further reduces the speed of the motor and increases its torque. Planetary gears are super cool, and this is the first time that we've come across them. So let's go on a little detour and appreciate their beauty. A planetary gear or epicyclic gear train is so called because it has planet gears orbiting around a sun. They have a couple of benefits, but one of the big benefits for us is that they're compact. So compact that from the outside, we wouldn't even realise that there's a gearbox in the motor. They're also strong, stable and efficient. In our system, we have a sun gear, which is driven by the electric motor. Around the sun gear are our planet gears. We have 3 planet gears, but we could have more or less. 3 just happens to be a nice number. The planet gears mesh on their outside with a ring gear, which in our starter is fixed. So, as we turn the sun gear, the planet gears all roll around the ring gear and orbit around the sun. To get power out of this system, we use the orbiting motion of the planet gears. A carrier with small shafts runs through each planet gear, linking them together and taking the rotation out at a greatly reduced speed and a higher torque. Now, one of the benefits of this system is that we have lots of teeth meshing at once. If this was just a pair of differently sized gears, then just a couple of teeth would be taking all the force. This way, the force is spread across multiple points and the gears can be made from weaker, cheaper materials. We've got a nylon ring and sintered gears. Calculating the gearing ratio of planetary gears is supposed to be complicated, tricky maths, but it's actually really, really easy. You just go on Google and you type in planetary gear ratio calculator and you'll find someone else has done the hard work for you, standing on the shoulders of giants. Now from this calculation, I can see that our planetary gear ratio is 6:1. So 6 rotations of our motor gives us 1 rotation of the carrier. So the gearbox reduces the speed by 6 times. And then we've got the ratio of the pinion and the flywheel, which takes things down another 14 times. So spinning our motor 84 times will turn the engine once. Okay. It's very common to find electric motors that incorporate a drive set like this because motors are most efficient at high revolutions. So you'll find gear sets like this inside drills, power tools and most electric motors. To turn this motor, we need a lot of electricity. If you get into a car with even a slightly flat battery, everything will seem fine until you go to start the engine. And that's because the starter motor is the single biggest user of power in the car. The radio, the headlights, the fuel pump, none of it even comes close to the power demands of the starter motor. The label on this starter motor shows that it will take a current of 400 amps. That depends on the load. On a cold day, with thick oil, it might take 400 amps, but normally it's probably around 100 amps, maybe 200 amps. So how does this motor compare to, for example, this beefy mains-powered compressor motor, or to a kettle? Well, we can't compare the current figure, that 400 amps, because a low voltage, like 12 volts, requires much more current than a higher voltage, like the 240 volts, that this motor takes. We need to calculate power, and power is measured in watts, and it's actually very easy to work out power. It's voltage times current, and it's a useful formula to know for all sorts of things around the garage or in the house. So the voltage is 12 volts and the current is 400 amps. So 400 times 12 gives us 4,800 watts, or 4.8 kilowatts. And that's a lot. A kettle takes about 1.2 kilowatts. So this starter can put out the power of 4 kettles. And this huge motor takes 2.2 kilowatts, which is surprising This small motor is double the power of this bigger one. And while we're comparing these two motors, notice the difference in design. This bigger motor is covered in cooling fins because powerful motors get hot. And even though the starter motor is more powerful, it doesn't really have any cooling fins. That's because it's intended to only run for a few seconds, not for hours like this beast. A starter is designed for bursts of high power and not endurance. The current requirements of a starter are going to vary. A starter for a bigger engine will need more power. Diesel engines have higher compression, so the motor needs to work harder there too. Starting a warm engine with thin oil is much easier than starting a cold engine on a cold day with thick oil. And a big diesel truck might well take 1000 amps for its starter motor. But even at 400 amps, getting the current to the starter motor needs a big fat supply cable, the thickest cable in the car generally. A cable will run straight from the battery to the starter. And if you want to find your starter, then just follow the thickest cable off the positive terminal. And the return path to the battery, because this is a circuit, is made via the engine itself. The negative side of our motor is connected to the metal motor body, which is connected to the engine. The battery's negative terminal is attached to the chassis, and the engine is connected to the chassis with one or more earthing straps, as we've seen before. Of course, the earthing straps need to be just as thick as the starter supply. At 12 volts and big currents, there's a huge voltage drop along the wires, so the cables to the starter motor should be as short as possible. Most cars have their battery in the engine bay, but in this particular car, the battery lives in the trunk because that improves the weight balance of this vehicle, because it tends to be front heavy with the engine and the gearbox and all the rest in the front of the car. So there's a long thick cable running from the battery to the starter. Okay, so we have the current into our starter and the motor is generating enough torque to actually spin the engine. But right now we don't have any way of turning the starter on and off. What we need is some sort of switch. There's a challenge here because we could haul this huge supply cable up into the dashboard, but then we'll need a massive switch on it like something out of Frankenstein.
It's coming up!
And big currents require big switches and chunky metal contacts. Routing this wire up into the dashboard would also double the length of the cable that we needed. And we just talked about voltage drop and really wanting short cables between the starter and the battery. So before drivers began worrying about their camel skin seats and hand-brushed aluminium interiors, a big clunky switch was exactly how the starter was operated, often a big metal foot switch. Nowadays, we want an elegant little key or even a push button that can activate the starter. And that's achieved by splitting the electrical supply into two separate circuits. A starter motor circuit, which carries the heavy currents to drive the motor, and a control circuit, which uses lighter wires that control the heavier circuit. And to do this, we use a solenoid. The principle behind the solenoid is that a small current is used to turn on a bigger current. And if you're familiar with relays, then it's exactly the same idea. A solenoid is simply a tight coil of wire that generates a magnetic field inside itself when it's powered on. That magnetic force will pull a piece of iron into its center. A starter solenoid uses this exact design, and here's one that I've cut open. You can see that there's a coil of wire running around inside, and inside that coil of wire fits a plunger. And when we turn on the current to the solenoid coil, this terminal is a positive, and like usual, the casing of the solenoid acts as the ground. As we turn on the current, the plunger is pulled in, and it's pulled in with quite a lot of force there, as you can see. When we release the current, the plunger pops back out. Now, at the end of the solenoid is a push button, which is just inside the coil. And when the plunger is pulled into the solenoid, it pushes on that switch, which connects the heavy current to the starter motor. On the back here we have two terminals, and one terminal brings power from the battery's positive terminal and the other terminal runs to the starter motor. And when the button is pushed, this big hefty piece of copper bridges the two copper terminals here, and that takes current to the starter. The starter runs. In some cases the plunger will directly bridge these terminals, but having the push button setup that we have here and the separate area where the contacts are made keeps any sparking or arcing in its own little area here. We've seen the two big terminals on the back of the solenoid, and there's a third smaller terminal here. And that third small terminal is used to turn the solenoid on and off. It's called the S wire or the S terminal, the S being for signal. And the wire from this small terminal leads up to the ignition switch. And as we said, with most electrical systems in the car, the solenoid is grounded via its casing, so we only need one wire to control it. A current flows down the signal wire, in around the solenoid coil, and then back to ground through the chassis of the vehicle. It's quite common for there to be two coils inside a solenoid, a strong closing coil that pulls in the plunger, and a second weaker coil which holds it in position, because it takes a lot more energy to pull the plunger from outside the coil into it than it does to hold it in position. And where the contacts for the starter are made, a switch also de-energizes that pull-in coil, so it saves a bit of power from the battery that's not needed when the starter is actually cranking. But don't worry about that, because if the solenoid coils aren't working, then you're replacing the whole solenoid, or probably the whole starter assembly. If you've ever tried to start a car with a flat battery, then you've probably heard a repeated clicking sound, this that's not clicking sound. Click, 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 click sound, and the engine doesn't start. And that clicking is the solenoid moving, or the plunger moving inside the solenoid. Now, with a good battery, the solenoid moves once to start the motor. So it moves inside, clicks, the motor runs, and if you listen carefully, you'll hear that click before the starter motor starts running, and it drowns it out with the whirring sound. But when the battery is discharged, there isn't enough power to supply the massive current that the starter motor needs. Now, the solenoid doesn't need much power, so it still plunges. And that turns on the starter motor. As soon as the motor's turned on, it takes all the current from the battery in an attempt to move. But there isn't enough current to power the motor, and there isn't enough current left, or isn't enough power left in the battery to hold the solenoid closed. So it's forced back open by the spring, and the motor's disconnected. But now, with the motor disconnected, there's enough power for the solenoid. So it plunges back in, energizes the motor. The motor can't run, but it takes all the power, solenoid pops out, and its process just continues. And that's the clicking that you hear as you attempt to start a car with a flat battery. So, if you're sitting in a car with a pack of velociraptors bearing down on you and the car won't start, you just hear this clicking noise, just think of the beauty of this solenoid mechanism. So far, we have a starter motor that can be switched on and off, and through the reduction in gearing, it has the torque to turn the engine over. And with this design, we can start the engine, but the engine runs much faster than the starter motor, and with the setup that we've already discussed, the starter motor would be permanently meshed with the flywheel. And after the engine has started, it would be driving the motor around in a situation called backdrive, where the flywheel is driving the starter motor. Now, driving the starter motor all the time would be a total waste of energy, but more importantly, it would tear this motor to pieces, because it's designed to do the driving and not to be driven. Take a look at the video of the starter in action from earlier. You can see the pinion engages the flywheel, then spins, and then disengages the flywheel when we release the ignition. The pinion moves in and out when the ignition key is turned on and off. Unfortunately for us, we already have something moving in and out when the starter is engaged. That's the plunger inside the solenoid. Now, you might have noticed that there's a small white pin on the plunger, and it hooks to a nylon lever, which I need. I go find this nylon lever. This pin on the plunger hooks to a nylon lever that pulls the pinion gear in and out. And this lever is a fork that fits over a ring on the shaft of the starter's drive gear. And the layout of the plunger and the fork mean that the pinion is moved into mesh with the flywheel just before the motor is turned on. This is called a pre-engagement system because the gears are engaged before the motor runs. As the pinion moves, sometimes we'll be lucky and the pinion teeth will fit into gaps on the flywheel, the ring teeth here. But we can equally be in a situation where the two gears clash and the teeth bang into each other. There are three ways that this situation is handled. The first is with a small bevel on the pinion gear here, which means that as it clashes here, it will tend to be guided, just a slight rotation to bring it into alignment. So if we're slightly misaligned here, then that small bevel will hopefully correct things. The second way that this clash of gears is handled is through a slight twisting in the pinion. So let's look again at the starter engaging in slow motion. Can you see that there's a slight rotation of the pinion as it moves along the shaft? That's achieved with this helical twist on the splines here on the armature. As the fork pushes the pinion assembly along, it rotates slightly on these splines, and combined with the bevel on the teeth, it's quite rare that the pinion won't engage, but it is still possible. And to handle this situation, the pin on the solenoid plunger has a spring. When the gears have collided and they're not interlocking, the plunger isn't going to make it all the way to the motor contacts. So the solenoid keeps pulling, and this spring is overcome, and it's a very strong spring, allowing the plunger to make it to the contacts and switch on the starter. As soon as the motor spins, our gears will pop into mesh and the flywheel can spin. It's brilliant. Now, we're almost there, but there's one final challenge that the starter needs to engineer around. What would happen if someone keeps the ignition key turned after the engine has started? At the moment, the starter would stay connected to the flywheel and it would be forced around by the engine until we release the ignition. Now, I'm sure you're all saying, oh, I've got super fast reflexes. I release the key immediately when the engine fires up. Well, what about your gran? Well, she's probably got super fast reflexes as well. But anyway, we only want the starter motor to be driven one way. The motor should turn the pinion, but the pinion should not turn the motor. And actually, what we want to happen is exactly the same as on a bicycle. You know, when you're on a bicycle, power from your feet should turn the wheel, but the wheel should not turn your feet. And this is achieved with a free hub on a bicycle. We don't even think about it, but it's a type of one-way clutch. Force only goes one way, from the pedals to the wheels. The starter motor also uses a one-way clutch, a design called a sprag clutch. It's this cylinder that looks like a bearing, and it looks like a bearing because basically that's what it is. There are a few different types of one-way clutch, but they all work on pretty much the same idea. The clutch is made up of an inner race and an outer race. The inner race is connected to the pinion and the outer race to the motor. The two races are separated with little wedges called cams or sprags. Turning the bearing one way causes these little sprags to rotate and get jammed, locking the inner race and the outer race together. So the outer race is now propelled around by the inner one. This is how the motor turns the pinion. But turning in the opposite direction makes the sprags rotate in the opposite direction too, and they don't bind up. The outer race is free to rotate, and since it isn't locked to the inner race, it can just freewheel. So when the pinion is running faster than the motor, this clutch stops the force being sent back to the starter motor. That's not quite everything. Every car built since about 2005 and many built before then will have what's called a starter safety switch or a neutral safety switch. This switch prevents the starter from running when the vehicle is in gear. And the idea behind that is that accidentally starting the car in gear would cause the vehicle to jump forwards and potentially set off driving on its own. Now, there's loads of reasons why this is bad. You might lurch forward a couple of feet and hit a car in front or a garage wall, or a kid left in the car could start the vehicle driving by messing around with the key. The safety switch sits between the ignition switch and the solenoid, keeping the circuit open unless the safety switch is engaged. On an automatic vehicle, this switch is on the transmission, and it's closed only if the transmission is in neutral or it's in park. mechanical switches for automatic vehicles also stop the ignition key from actually turning in the barrel, and those are called interlock switches. With a manual vehicle like this one, the switch will be on the clutch pedal, and it only actuates when the pedal is fully depressed. There's often another switch on the clutch pedal for the ECU, and that ECU switch makes contact as soon as the clutch is pressed, even slightly. So if you're rummaging around down in the footwell checking the clutch safety switch, just be sure that you've got the right switch. Let's take a look at the starter system as a whole. When you turn the ignition key, that acts like a switch, and current flows through that switch to some sort of safety switch, either on the clutch pedal or on the transmission. The safety switch stops the car being started in gear, and with the ignition and safety switch closed, power goes to the solenoid. When the solenoid is engaged, it pulls a plunger. The plunger uses a lever which pushes the pinion into mesh with the flywheel, and when the pinion is engaged, the plunger moves a bit further and switches on the current to the starter motor. The starter motor runs, starting the engine, and when the ignition key is released, a strong spring in the solenoid pushes the plunger back out, turning off the starter motor and retracting the pinion from the flywheel. So we got through a lot there. We'll come across planetary gears again on the differential. We'll meet solenoids on various valves and actuators elsewhere around the car, although if someone talks about a solenoid in relation to a car, they're almost certainly going to mean the starter solenoid. And one-way clutches, well, they're just cool, but they're also found in automatic transmissions. And of course, you know absolutely everything about starter motors. Now the starter uses a load of power from the battery, and we need some way to recharge that battery once the engine is running. So next we'll talk about the alternator and how it generates electricity.